Hey physics nerds! This is the video on the PowerPoint lesson I gave that one day in which we talked about magnetism. And this is a long-awaited video. I know some of you guys were absent that day, and I promised a video, and here it is. Anyway, you should have obtained the worksheet that accompanies this. If you did not, you could always grab it from the lab assignment on Pupil Path. Yes, the document that goes with this lesson will be on the lab assignment on Pupil Path. Look for the magnetism lab assignment. Okay. Anyway, this PowerPoint will be going through much of what I taught in class on magnetism. The majority of it you kind of don't need to know, but I still think it's very interesting and cool to know anyway. But there's still a lot of key points that you need to know, and I'll highlight them along the way. I'll emphasize it. Anyway, let's start. In essence, magnetism is a force caused by moving charges. That's the big point here. Magnetism is a force caused by moving charges. And here we have two main types of magnets that we dealt with in class. The permanent magnet and the electromagnet. Permanent magnets are probably what you're more familiar with. They're those bar magnets or those things you see on a refrigerator. The horseshoe magnet is another classic example. These are pretty much, in those cases, the moving charges are the orbits of electrons spinning around the nuclei. I'll elaborate more on that later. Now, the other type is electromagnets. This is the kind we made in class using a circuit, based on the current providing the moving charges. Here are some classic images of a permanent magnet and an electromagnet. The horseshoe magnet, as I said, is an example of a permanent magnet, in which the magnetic field is permanently set. There's no way to change it unless you're looking at an electromagnet right here on the right side. This is what we made in lab. We attached a battery, hooked up some wires, created a circuit, connected everything. We connected the wires, the alligator clips, to a nail with a copper leads wire, copper wire, wrapped around and coiled around an iron nail, in which we connected to the circuit, and using the nail we created a magnet. So this slide I talk a lot about permanent magnets. Here it's the magnetism produced by electrons orbiting around the nucleus. So they have what is called the magnetic moment, induced by the spin of electrons and other elementary particles, mostly the electrons. So let's imagine the inside of an atom. The nucleus at the center, and then you have electrons orbiting around. We don't know whatever pattern they're orbiting around, but as they're orbiting around, moving around the nucleus, they're also spinning. And because of that spin, they have that magnetic moment I was talking about. And so permanent magnets can also be artificially created by magnetizing ferromagnetic materials. So examples of ferromagnetic materials are right here: cobalt, iron, nickel. Iron is a very common ferromagnetic material often used, especially like iron nails. That's what we use in lab. We use an iron nail, wrap some copper wire around it to produce our electromagnet. So it's these specific materials that are just naturally have this property. Now, as for this electromagnet, the moving charges are pretty much produced based on the current running through the circuit. So if a current is running through a wire coiled around a ferromagnetic core, and an example is our iron nail, then a magnetic field can be produced. So you see here, magnetic field is being produced because of the current wrapping around this iron core. And so we can use the right hand rule. So I want you to raise your right hand here. You're going to have honestly, you guys can't even see this, but if you take your right hand and curl your fingers around the nail in the direction of the current. So notice here, I'm highlighting the direction of the arrow, so it's curling around in this direction. I want you to curl your fingers around that. And look at the direction in which your thumb is pointing. Your thumb will always point in the North Pole direction. So if you're doing this correctly, your thumb should be pointing upward in the North Pole direction, as indicated by the image here. Now, if the current were going the other way around, your thumb will be pointing southward. That's the right hand rule. And in this last bullet point, our magnetism lab will also... Oh my god, this is not even grammatically correct. Our magnetism lab will also involve the creation of an electromagnet using a circuit, basically. Wow. I should proofread these beforehand. There's a little fun history about the history of magnetism. Ancient people learned about magnetism from lodestones. These are naturally magnetized pieces of iron ore. They're pretty mystical in the fact that these things kind of not so much levitated, but they kind of just like moved and suspended on their own, and they turned around, and because of that it had this mystical property, and the early ancient people have used this to be their first magnetic compass to direct them in certain directions, basically, for navigation purposes, basically. And the word magnetism comes from Magnesia, which is a place in ancient times where people have discovered these lodestones. So here's about magnetic fields. Thinking about how we drew electric fields, we could also draw out magnetic fields. They are polarized with two opposite ends, a north and a south pole. So these lines we draw are called magnetic flux lines. They're always coming out of the north and into the south. So you draw them coming out of the north and into the south pole. So just like electric charges, opposites attract and like poles repel. So here's a fun question. What happens if you slice this magnet in half? Do we have only north pole and only a south pole? No, you're still going to have a north and a south pole, north and a south pole with these two separate pieces. You can never slice a magnet in half and expect to have two separate poles. You'll still have a north and a south pole regardless. So here's this checkboard question at the bottom of the front side of that page I gave you guys. So which statement describes the gravitational force and the magnetic force acting on magnet A due to magnet B? So here these two magnets are suspended in, well, magnet A is suspended above magnet B. And we got to think about how. So because it's suspended, here we're in equilibrium. That means our forces up and down are equal and canceling out. The up and down force cancel out. Gravity will always pull downward towards. So that means the magnetic force, on the other hand, it has to point upward to counteract this. So F capital B is often what we use to indicate magnetic forces. For some strange reason, I don't remember. So what does this mean? The gravitational force is going to pull it down, causing an attraction, whereas the magnetic force has to push it up, which means it's a repulsion. In that case, our answer is choice 1. Remember that gravity is always attractive. Now the Earth's magnetic field. If you guys take a look at your compasses, the compasses will always point towards the North Pole. That means the magnetic North Pole on the compass is attracted to the Earth's geographic North Pole. But don't opposites attract? So that means the Earth's geographic North Pole is really a magnetic South Pole. So that's important, a fun, important thing to know. Plus, let's also think about the Earth. What is the Earth's core made out of? Iron. So basically the Earth is this one big giant magnet that's tilted on its side and it spins around. Hey, it's a magnet. Okay, let's draw this big Mother Earth. Okay. So I'm going to use different colors here. So let's put our geographic North and South Pole. I'm going to use another color to indicate the magnetic poles. And so, we're always going to draw our magnetic field going from out of the North and into the South Pole. Out of the North Pole and into the South Pole. Woo! It kind of looks just like this. This is really ugly, but bear with me, guys. But that's it. Now, let's breeze through this first question. You have two pieces of iron. One of them, or both of them, might be a magnet. So you take these two pieces together. You bring them together, they attract. Now, let's say you take one of those pieces, you flip it around. See what happens. They still attract. What does this mean? That means one of these objects has to be a magnet. The other one, not so much. It's not a magnet. Because what happens if you had two magnets? You put them together, north and south, they attract. Now, if you flip the other one around, you probably would have a north-north or a south-south touching, and they would repel. But in our scenario, you saw that they attracted. Because they attracted, that means one of them is not a magnet. It'll attract any other piece of metal anyway. So here, we can conclude that one of them is a magnet, the other one is just a piece of metal, piece of iron. Alright, question 2. In order to produce a magnetic field, an electric charge must be moving. Question 3. Which statement describes the polarity of magnetic poles A and B? Oh, this is supposed to have with an image. Anyway, I think it looks like this. Oops. So I'm going to draw what it looks like. This image, this diagram. So it looks like this, if I recall from the diagram. So that's what happens. So what does this mean? If it's coming out of A and going into B, that means A is north and B is south. And finally, we reached the end of this video. I hope my voice wasn't too annoying. I should really count the number of times I cough. So the next video I make, probably right after this, I'll probably keep a counter of how many times I cough. My throat is sore. Have a good night, guys. Study up for that IA. Good night.